Decision trees. A decision tree is an upside-down tree-shaped diagram that is used to determine a course of action. It consists of nodes and arrows, starting from the root node as the tree is upside down and branching out to the leaves, the final nodes that you see here. These are called the terminal nodes or the leaves of the tree. The nodes in between that the arrows come into and the arrows come out to, they are called decision trees. At these nodes, we have features and some conditions based on those features that the decision is going to branch out to new nodes. We can see that there are the branches. When the tree branches out, we can see subtrees or the branch of a tree as we see here. For example, this is a subtree or a branch. In this subtree or branch, this node is the parent node, and these two nodes are the children or the leaf nodes. The goal here is to find features out of many features that we have in these decision nodes, finding the most important features so that based on some conditions and decision making that we set up for on these decision nodes, we can actually classify our problems. Or it can also be used for regression problem to make a prediction for a continuous variable. To understand how decision trees work, let's play a game. In this game, I think about an object out of a set of objects that we are both aware of. You have to ask yes or no question to get to the item that I am thinking about. One simple way, of course, is to ask all the items or objects. For example, you could ask, is it a dog? Is it the elephant? Is it the bird? Etc. etc. This is a very easy one to do, but not very smart. Also, it's not going to be practical if you have a lot of objects to think about. So what should you do? You should think about qualities of these objects that can easily distinguish them from each other, so that by asking as little question, as few questions as possible, you get to the answer. For example, what qualities can we think about? Well, being alive or not. These three objects are alive and these three objects are not. So by asking those questions, you can actually get rid of half of the options. So for example, you would ask, is it alive? And I'm thinking about the car. So I would say, no, it is not alive. So the three objects on the right are going to be eliminated. So now instead of 6 objects, you can think about asking question to get to the answer, having a smaller set, which consists of 3 objects. What other question can you ask? So for example, you can ask whether it flies, or also another quality is its size. So by asking these 3 questions, whether it's alive, does it fly, or does it carry more than 10 people, you get to the answer, because the car that I was thinking about does not fly, it is not alive, it does not fly, and it does not carry more than 10 people. That's the only object here out of these 6 that has this quality. Not alive, doesn't fly, and doesn't carry more than 10 people. Sounds very simple, and that's the essence of decision tree. How to build a decision tree? The most important decision that you would have to make when you want to build a decision tree are the following. Selecting features to use for classification. Considering that you might have a lot of features to select from, it is important to select what features to use for decision tree. This is equivalent of what question should you ask in our previous game. Next is the conditions for splitting. After you picked your features for splitting or branching out, what should you set the conditions? For example, greater than, the feature should be greater than what value or less than what value. Next is, when should you stop? How far should you branch out? Or in our previous game example, how many questions should you ask? And last is a concept called pruning. Pruning is enforcing restriction on the tree to avoid overfitting. For example, you can set a maximum for the number of leaf nodes. So basically, pruning is a method that is used to simplify a complex tree that suffers from overfitting. It usually involves any measures that would restrict the size of your tree. For example, the depth of the tree, how many branches you would have. Decision trees for numerical data. So the example that we played, again, we were working with categorical data. Elephants, birds, plane, buses. What if we are working with numerical data? How can we develop a decision tree for numerical data? Let's see an example. In this example, we have two features, x1 and x2. And we have 5 classes here. One class is here, another class is here, another class is here, another class, and the last class. I'm going to name these classes. Class 1, 2, class 3, 4, and 5. 5 classes. How can we use a decision tree to classify these 5 classes based on the 2 features that we have? Well, this doesn't look really difficult if you look closely. Let's see how we can classify this. For example, class 1 and 2 can be separated from the other 3 classes by a specification of the x1 value. Suppose this is 20. So class 1 and 2 have x1 less than 20, and class 3, 4, and 5 have x1 greater than 20. We can further specify class 1 and 2, distinguish them from each other by setting a value for x2. For example, here. Suppose this is 50. So class 1 has a value of x2 less than 50, and class 2 has a value of x2 greater than 50. So using x1 and x2 here, values of 20 and 50, we can distinguish class 1 and 2 from each other. Let's now do the same for class 3, 4, and 5. To distinguish class 3, we can just use x1. For example, this line limit here can specify class 3. Suppose this is 25. So class 3 is the only class here that x1 value is between 20 and 25. Now we can classify and specify or distinguish class 4 and 5 by setting a value based on x2. Suppose this is 30 for x2. So now class 4 and 5 can be distinguished from the others by x1 and x2 values. Right, so how to build a decision tree? Well, we're going to do the same thing. The features that we have here, x1 and x2, and the question, the condition that we set, less than 20, x1 less than 20, x1 less than 25, and also x2 less than 50 or greater than 30, is going to be our question to ask if we were playing a game. In decision tree, it's going to be the conditions on branching. So we start with the root node. We started with the feature x1. Is x1 less than 20? Answering this question can specify or distinguish the two classes on the left, class 1 and class 2, from class 3, 4, and 5. Suppose the answer is yes. Then we would ask, is x2 less than 50? If yes, then we have class 1. If no, then we have class 2. Then we go back to our root node. If the answer to whether x1 is less than 20 is no, then we have class 3, class 4, and class 5. These three classes have x1 greater than 20. Now we can specify or distinguish class 3 from the others by asking a question about another x1 value, that's 25. So we would ask, is x1 less than 25? If the answer is yes, then we have class 3. If the answer is no, then you have to specify which classes is it based on the value as x2. So we would ask whether the x2 value is greater than 30 or less than 30. If it's less than 30, then it's class 5. If it's greater than 30, then it's class 4. And this is how a decision tree would work for numerical values with numerical features. Feature importance. When using a decision tree for classification, using different features for branching out would yield different results. This is a comparison to the play game that we did. There are a lot of questions that you could ask about the objects, the quality of objects, that you would help you to get to the solution, the object that I had in mind. Some of those features or quality that you would ask question for are more important and would get you to the solution to the object that I had in mind faster and quicker. This is similarly true in decision tree. Some of the features are more important and more effective to get to the classification result that we want faster and more productive. So features importance or effect on prediction accuracy can vary from feature to feature. Feature importance is a value between 0 and 1 for each feature. A feature with importance value of 0 is the least important feature that was never used in prediction. On the other hand, a feature with importance value of 1 is the most important feature that is used to correctly predict the target variable. Feature importance values are normalized, so they all would add up to 1. That's why we have all the feature importance values between 0 to 1. You can have access to the feature importance of your decision tree using this code of line. Your model, the name of your model, then feature underscore importance underscore. Make sure to do not miss the last underscore. This is how you can access to the feature importance of the features in your decision tree after you created it in Scikit-Learn. Key parameters of decision trees. Decision trees are very powerful machine learning algorithms, but also very susceptible to noises and overfitting. To avoid this, there are certain parameters that you can use to control the behavior of decision trees. One of them is max depths. Max depths control the maximum depths or the number of splits points in your decision tree. Basically, it means how much you want to grow your tree, branch after branch after branch, or nodes after nodes after nodes, or subtrees. Max depth is the most common way to reduce complexity and avoid overfitting. The other parameter is mean samples leave. So if you are at a certain node in the decision tree and you are wondering whether should you split more and go down deeper, you can set this to have that node to have the minimum number of instances or samples, and that would be for a leaf. So if a node has less than that, then you should leave it as it is and should not branch out. Otherwise, if you have more instances and that node, then you can split and branch out. This is another way to control the complexity of the decision tree and avoid overfitting. The other parameter is max leaf node. This parameter limits the total number of leaves that you want your tree to have. When you branch out and your tree grows and grows, you're going to end up having the end nodes or the terminal nodes at the very end of your trees. You're going to get more and more when your tree grows and grows more. So you can basically set a limit to how much leaf or how much grows your tree you want to have. Generally, in practice, adjusting only one of these parameters would be enough and sufficient.